Hi, this is Bill Reese, and in this video, we're going to be looking at the spreadsheet that is titled "The Efficient Frontier for 8 Stocks," which is an important spreadsheet because it does a whole lot of different things. So let me pull it up, and we will start to work on it. All right, so here is the first page of the spreadsheet here. And what I've done is I've selected 8 just different random stocks that are kind of well known. Okay, so these are their ticker symbols, PZZA, that's Papa John's Pizza. We've got Apple, Prudential, Disney, General Electric, Merck, ExxonMobil, and United Airlines. Those are our 8 stocks. IVV is an exchange traded fund that tracks the S&P 500. So the prices that you see for IVV are going to be 1/10 of the closing values for the S&P 500 each of those days, and the returns for IVV are going to be with, I think, like 99.5% accuracy, something like that, track the returns on the S&P 500. So that is going to be our proxy for the market here. Okay. So what I've done is I've used the stock history function, okay, to get the prices at the closing prices at the end of each month from December of 2019 through December of 2024. So here's the end of December of 2019 where Papa John's was. Here's the end of January 2020 and so forth, all the way down here. Here's the end of December 2024. Then over here, what we're doing is we're calculating the returns for each month using continuous compounding. So this is the natural log of the price at the end of January divided by the price at the end of December. So from the end of December to the end of January, of course, that was the return during the month of January. So during the month of January of 2020, Papa John's was up by 2.55%. Apple was up by 5.26%. United Airlines, that wasn't a good time for them. They're down by 16.35%. But you might remember the January of 2020 is when we first started to get some indication that there's this strange little virus coming out of China, right? And as we see a little bit later on, United Airlines in March goes down by 66%. But anyway, that's not the purpose of this. It's just to get those 5 years ending at the end of 2024. So we've got all the returns here. This is the S&P 500 returns, and these are the returns for each of these stocks we've got there. Now, for convenience sake, what I've done is I have used the name manager to name the returns. For example, these returns on Apple are named AAPL. Now, if you've never used name manager, my suggestion is learn how to do it. It can be helpful for things. That's not the purpose of this video, and you don't need to know that for this course, but I think it helps to work on things. But whenever you see AAPL, Excel interprets it as being these numbers right there, those cells that are the returns on Apple there. Okay, so what we've got down here is we're using the standard deviation function to give us the monthly standard deviation of Papa John's, okay? And this is standard deviation of a sample, STDEV. And you can see it is the standard deviation of the cells that are named PZZA. Here's the standard deviation of Apple, standard deviation of Prudential, and so forth all across there. Now, because we are going to be using both expected returns and standard deviations, and expected returns we always think about in terms of annual numbers, we need to annualize our monthly standard deviations. See, these were all monthly numbers, so calculating the standard deviation is the monthly standard deviation. How do you annualize it? You multiply by the square root of 12. If you have monthly variance, you multiply by 12 to annualize it. If you have monthly standard deviations, you multiply by the square root of 12 to annualize it. Now, this is not how you annualize returns. That's totally different. We don't need to get into that right now. But to annualize monthly standard deviations, you multiply by the square root of 12. So these are all our annualized standard deviations. Now, of course, this was for this 5-year period, and we know that that does not necessarily mean that's what they're going to be in the future, but we're going to make that assumption right now, okay? And then we'll talk more later about the fact that that what has happened in the past may not be what happens in the future. Here, what we're doing is we're finding the correlation between each of these stocks and the S&P 500. So here's the correlation between Papa John's and IVV. Here's the correlation between Apple and IVV, okay, at 0.7588 and so forth there. So for each of these stocks, you got the correlations. Of course, we're always looking at the correlations between the returns, not the correlations of the prices. Then we're calculating the beta. Okay, so to calculate the beta, there's several ways we could do this. Okay, the way I've done it right here, we've said the beta is going to be the correlation between the stock and the S&P 500 or the market. Okay, divided by the standard deviation of the stock, divided by the standard deviation of the market. So that's what we've got right here. That's going to be the correlation between the Papa John's and the market, multiplied by the ratio of their two standard deviations, standard deviation of Papa John's divided by the standard deviation of the market. That's giving us our beta for Papa John's. Here's the beta for Apple, et cetera there. And of course, the beta for the market is always going to be 1. And then we're using the CAPM, okay, the capital asset pricing model to find the expected return for each of these stocks. So we've got a risk-free rate. I'm just setting the risk-free rate at 3% right here. We would want to say what is the current risk-free rate, but we're just going to set that at 3% because when you're viewing this video, the current risk-free rate may be different than what it is when I'm making the video here. So we're just going to set that at 3%. And I'm going to set the market risk premium at 5.7%. So using those values, here's with the capital asset pricing model, here's the expected return for each of these 8 stocks down here. And of course, then here is the expected return for the market. Then we are putting together an 8x8 correlation matrix. Here's the 8x8 correlation matrix. All the correlation between Papa John's and itself is 1. The correlation between Apple and itself is 1, and so forth. Here's the correlation between Papa John's and Disney. Okay. Here's the correlation between Prudential and Merck and so forth there. So this is calculating the correlation. Everything that you see down here, down in this area, it's got the exact same thing up in there. Okay. And so here is the standard deviations of each of these. Here are the expected returns, just reading from the prior page. Then what we've got here is an 8x8 variance covariance matrix. This is the variance of Papa John's. How do we get that? Well, we took the correlation of Papa John's with itself, which of course is 1, and multiplied that by the standard deviation of Papa John's times the standard deviation of Papa John's. So standard deviation squared is, of course, the variance. On here, to get the covariance between Papa John's and Apple, what are we doing? We're taking the correlation between Papa John's and Apple times the standard deviation of Papa John's times the standard deviation of Apple. There are other ways you can calculate variances and covariance. This is not, the only way or necessarily even the best way. It's just a way that works well for me. Everything that is down here is also going to be up here as well. So everything on the diagonal, those 8 cells are variance terms. Everything in the off diagonal, all the cells down here and all the cells up here, those will be covariance terms. Okay, so it's an 8x8 variance covariance. No weightings in there yet, just variance covariance matrix. So we go over here, and this is just duplicating it. The exact same thing we saw. I just wanted it on this tab here. So there is our variance covariance matrix. Now, what we're doing here is we're going to be establishing a weighted variance covariance matrix where we're going to use solver to solve for the weights. So this right here is going to be our 8 by 8 weighted variance covariance matrix. These right here are going to be the weights. Okay. Solver is going to solve for those weights. This right here is going to be equal to this right here. This is the weight, going to be the weight on Papa John's. Whatever is there is also going to go here. This is going to be the weight on Apple. Whatever goes there is also going to go there. Down here is the weight on United Airlines. Whatever goes there is also going to go up here. So these are weights up here exactly as these are weights down there. And again, where do they come from? You'll find out in a little bit. We're going to get them from Solver. This is an important cell. This says, what do the weights add up to? Okay. And the number one is not typed in here. Okay. The number one is solved for. Okay. So all these numbers, these weights do add up to 1. We will always want the weights to add up to 1. You do not type the number 1 in there. You leave this formula there, and we're going to set in Solver that that is a constraint that the weights have to add up to 1. Okay, we'll see that in a minute here. Now, this is the variance of the portfolio. Okay, how do you find the variance of a portfolio? Very important. It is the sum of all the cells in the weighted variance covariance matrix. There you go. There's all 64 cells in our weighted variance covariance matrix. You add them up, there's the variance of the portfolio. What's the standard deviation of the portfolio? Square root of the variance of the portfolio. So with these particular weights, the standard deviation of the portfolio is this number. What's the expected return of the portfolio? Well, we're using the sum product function here, which is going to be, it means to take this times this, plus this times this, plus this times this, plus this times this. So you need two different arrays of cells, okay, that are that you're doing this times this, plus this times this, plus this times this. And it's going to be our weights right here multiplied by our expected returns, which were back here. Okay, so we're going to do the weight on Papa John's times the expected return on Papa John's, plus the weight on Apple times the expected return on Apple, plus the weight on Prudential times the expected return on Prudential, and so forth there. So that's what we're doing. It's doing these weights times those expected returns, and that gives us the expected return on the portfolio. So when we change the weights around, of course, that's going to change the values in the weighted variance covariance matrix, which is going to change the variance of the portfolio and change the standard deviation of the portfolio, and it will change the expected return of the portfolio. Let's make a change here. Let's create an equally weighted portfolio. Equally weighted portfolio is where we've got the same weight on each of the stocks. Since I've got 8 stocks, let's put a weight of 1/8 on each one of them. So let's start right here, and we're going to say that weight is going to equal 1/8. Okay, so we put a weight of 1/8 on Papa John's, and let's scroll this down, okay, so that we're putting a weight of 1/8 on each of the stocks. So 0.125 is 1/8. So each of these stocks has a weight of 1/8, and you can see the weights are up there as well. And this cell right there, again, the number 1 is not typed in. That's saying, what do we get when we add up those weights? Well, if you add 8 of the 1/8, of course, you get 1, a weight of 1. So now that has changed all of these cells in here. And of course, it has changed the weights that are used to find the expected return on the portfolio. So for an equally weighted portfolio, these 8 stocks, the standard deviation of the portfolio is 24.32%. The expected return of the portfolio is 9.47%. Well, here's what we want to do. We want to ask Solver to find the smallest possible standard deviation, okay, for expected returns of 2%, 3%, 4%, 5%, 6%, and so forth, all the way through there. We want to say to Solver, find for us the the hyperbola, okay, which contains the efficient frontier on it. Okay, now technically the efficient frontier starts with the minimum variance portfolio, but some people call the whole hyperbola the efficient frontier, and that's fine if they do. But here's what we're going to be finding. Okay, we're going to go over here, and this is the hyperbola. We're going to actually be creating that. It's already done for us here, but we're going to see how that is actually done. The way it is going to be done is we're going to say, hey, for an expected return of 2%, what is the smallest possible standard deviation you can get from these 8 stocks? And what are the weights on the 8 stocks? Well, what we're going to do is we're going to see that Solver is going to tell us the smallest standard deviation we can get is 32.56%. And these are the weights that do it. It's got we're shorting Papa John's by about 1.5%. We've got, looks like about 9, almost 10% of our money into Apple. We got a little bit of a short. We got a big short there on Prudential, 47% short on Disney. We got some 17.8% into General Electric, et cetera. That with these weights, again, we haven't solved for these yet. We're going to see how to do it in a second. That gives us an expected return of exactly 2%. And that gives us the smallest possible standard deviation for an expected return of 2%, which is going to be read on this graph, come right here. That's going to say, hey, for an expected return of 2%, the smallest standard deviation you can get is right there at 32.56%. You can probably work it out to get a higher standard deviation than that, but that's the lowest one. You can't get a standard deviation down here for an expected return of 2%. So what we're going to end up doing is we're going to solve for each one of these. I'm not going to do each one of them in the video. We're going to do a couple of them, and then you will get the opportunity to be able to do the rest of them to confirm that you know how to do them. And we'll see that this graph here just picks that up once we have got the values in here. Then we will also find for the minimum variance portfolio and the mean variance efficient portfolio as well. Solver is going to help us with this. So what do we got in here? These are all the individual stocks, okay? PZZA, that's Papa John's. There's the expected return and standard deviation for Papa John's. Okay, right over here is Apple, the expected return, standard deviation for Apple, and so forth. So we've got them all in there. And then we've also got here IVV, which is the S&P 500, which is to the left of this hyperbola. And by the way, that's because we're not using the S&P 500 in this portfolio of these 8 stocks. We only used it to help us find the expected returns with the capital asset pricing model. So at any rate, let's go back over here, and we're going to say to Solver, find us the smallest standard deviation we can get for an expected return of 2%. So here's Solver. And our objective here is going to be our standard deviation. And what are we going to do? We want to minimize it. And what do we want to change? We want to change these weights. Okay, the weights on those 8 stocks. And of course, when those change, it will automatically change them up there on row 14. Okay, so we're saying change those weights to give us the smallest possible standard deviation. There's 2 important constraints. One is already in here, that is cell B23 has to equal 1. In other words, the weights are going to have to add up to 1. What's in that cell right now is equals the sum of the weights. So we want the sum of the weights to add up to 1. That's what that constraint is going to do for us there. And now we're also going to add a constraint that the expected return has to be 2%. So we're going to go over here, hit add. And we're going to say the cell is going to be right there, expected return. And that cell must be exactly equal to 0.02 or 2%. So we hit OK. And we see that show up as a constraint here. Okay, so we've got 2 constraints. One is that the weights have to add up to 1. The second one is that the expected return has to equal 2%. So it would take us, and I'm not kidding on this, a week, okay, to try different weights onto these things randomly, these 8 stocks, to try to find the exact weights that give us the lowest possible standard deviation with exactly an expected return of 2%, and that the weights add up to be exactly 1.0. But Solver works at the speed of light, so it'll find it in just an instant. So we hit solve, and we've got a solution here, okay? We hit OK, and here it is. With these weights right here, okay, we're going to get a standard deviation of the portfolio of 32.56%. Notice the weights have added up to 1, okay? So we have not made money appear or disappear. We've just worked with the money we have. And notice that the expected return equals 2%. You don't type in 2%, okay? You say here that the weights, okay, multiplied by the expected returns has to equal 2%. And they do. These weights have been set up so that they exactly will end up being an expected return for the portfolio of 2%. And the weights will add up to exactly 1. And the weights are going to give us the smallest possible standard deviation to the portfolio here. So what we're going to do here is we are going to do some copies and pastes, okay? We're going to take this standard deviation right here, and we're going to copy it. What's the best way to copy it? You have this different ways, but I'm going to hit Control-C, okay? And then to paste it, I go over here, okay? And it's already there, but what I would do to paste it is I would go right there, and I would go to Home, and I would want to do a paste special, because otherwise it'll paste the formula, and you don't want that. To do paste special, paste values, you do right there. You just click on that as a percentage, and there it goes in there, okay? Then we want these values. And by the way, look at these values that were already there. They're the exact numbers that we just got, because hey, I already did this beforehand. So we would go back over here, okay, if that wasn't already done for us, and I would highlight these right there. And again, I would hit Control-C to copy them. I would go over here, and I would place my cursor right there. And now I would go paste value, but I don't want them as percentages. I want them as numbers. So I would hit the control of my paste special over there, and it gives those values. Now, what is happening is this graph here is reading these two numbers, okay, to give us this dot right there, okay? You're not going to have to do graphing in this class, okay? But I would recommend, okay, that you learn. It's worthwhile to do, and you could just learn by kind of studying how it was done here, okay? But you're not going to actually have to do it. So at any rate, now we have found this point on the efficient frontier, okay? Which again, technically, the efficient frontier starts right up in here at the minimum variance portfolio. But let's just say that point on the hyperbola then, okay? So we're going to go back over here, and we say, let's find the next point. Let's find what is the smallest standard deviation we can get for an expected return of 3%. So this is going to be fairly easy for us. All we need to do is go over here to Data, to Solver, and everything's already set up. We want to, my objective cell is still standard deviation. I want to minimize it. I still want to change these 7 weights. I still want the expected return to be 1, but now this constraint is going to change, okay? Instead of the expected return being set for 2%, I want to change it to 3%. So we hit change, okay? And I'm going to change it so that it equals 0.03. Okay, hit OK. That's telling Solver, okay, I want you to go back and do this all over again. Change the weights. They still have to add up to 1, but I want you to give me the smallest possible standard deviation for an expected return of 3%. And the weights have to be such that it gives us an expected return of exactly 3%. And again, working at the speed of light, Solver will find it for us just like that. And it does. Okay, so here is our answer. The expected return of the portfolio is now 3%, and the weights are a little bit different, what we've got there. So what would I do? I would copy and paste again, okay, which I'm not going to do it again because I've already got those numbers there. Notice the standard deviation of the portfolio is 28.12%, and here it's already been done. And these weights here are the exact same weights as we just ended up doing. So we did it for 2%, we do it for 3%. Then you go back and you do it for 4, 5, 6. And as you do all of them, guess what? We get this nice hyperbola that's there. and we say that these are the smallest standard deviations you can get for each of these expected returns. We call that portfolio optimization because this is optimized, okay? To be able to, if you say, hey, I want the smallest standard deviation, I want the least risk for the most return, okay? Well, for any of these given returns, expected returns from 2% to 13%, this is it. This is how you get the least amount of risk with these particular weights that are there on these 8 stocks. Remember, there's only 8 stocks that we are looking at. Now, suppose we want to find what is the minimum variance portfolio, okay? It turns out that it's something we've already solved for, okay? It's 7%. That's just kind of a coincidence. It's actually a little bit above 7%, okay? 7.0001% there. But let's see how that would work. Okay, that's a little bit unusual that it's exactly one of those integers, but that's the way it worked out here. So the way I would do this is I would go back over here, hit solver, and I would just remove this constraint entirely. I would say, hey, find me the smallest possible standard deviation by changing the weights. The weights still have to add up to 1, but expected return can be anything. Okay, so if we do that, we hit solve, we got the answer. And guess what? There's our answer, 7%, which actually ends up being like 7.001 or something like that, with a standard deviation of 17.65%. That is the MVP, the minimum variance portfolio, because I asked Solver to say, what are the weights that give us the smallest standard deviation under any circumstances, under any expected return? And so last thing we want to take a look at here in this video is going to be what is the MVE. The MVE is the mean variance efficient portfolio. That is going to be the portfolio that maximizes the Sharpe ratio. So we're going to go back over here and we're going to say, all right, here is the risk-free rate, okay, 3%. Here is this happens to be the expected return of whatever I already have here, okay? Whatever is showing up there in cell B27, that's what I've got here, okay? And the standard deviation is going to be whatever I have there in cell B26. So I'm going to be changing these weights, which will change this expected return, change this standard deviation, which will change this expected return and this standard deviation. And these will be used then to give me the Sharpe ratio. The Sharpe ratio is going to be the expected return. Okay, let's take a look at it. The expected return minus the risk-free rate divided by the standard deviation of the portfolio. Okay, so I want to get that as high as possible. Okay, I want to maximize it. So I'm going to say to solver, change these weights, which will change, of course, the standard deviation of the portfolio, the expected return of the portfolio, which will be changing these numbers right there, which will make this number right there as high as possible. So let's go to solver. And this time I want my Sharpe ratio to be what I'm working with. I want to maximize it. This stays the same. I'm changing the weights on those 7 stocks. I still want the weights still have to add up to 1, okay? And there's no other constraints, okay? I don't want the expected return to be a specific value or the standard deviation to be a specific value. I'm saying, hey, get these weights whatever they need to be to maximize the Sharpe ratio. And that's what we're doing right there. In cell M14, that's the Sharpe ratio. So we hit solve and solver says, we've got a solution for you. And here it is, okay? We cannot get a Sharpe ratio higher than 0.2912, whatever it is there, okay? That when we have these weights on those 7 assets, it gives us an expected return of 9.61%, standard deviation 22.68%. And that, there we see them right there, with a risk-free rate of 3%, it gives us, that is our Sharpe ratio as high as it can possibly be there. And so what would we do? We would copy and paste it so that it is down here. Here it is again. Those are the numbers that we just had there. And that's being read by, guess what? By this graph. And so here is our MVE, this point right there. And this is the capital allocation line that goes through the MVE right there. And so does it look like it's tangent? Yeah, sure does to me. So things probably worked out okay. I think those are the correct numbers. Otherwise, this is the same hyperbola that we saw up here, but now we have the MVE has been found, and we're actually graphing that out. Now, I'm not going to take the time to go through it, but you might want to, okay? We can also find out where a particular investor will choose to be on that capital allocation line by putting their A, their coefficient of risk aversion in here, and having a solver solve for what is the weight on the MVE, and then what is the weight on the risk-free asset in order to maximize utility. But this is really the same thing we did earlier when we looked at maximizing utility with one risky asset and the risk-free rate. So, but you can do it in here. I would encourage you to maybe do it yourself and see what you get through that. Of course, you're going to get different points on that capital allocation line depending upon what you select as the A, as the coefficient of risk aversion there. Okay. So we have drawn our hyperbola here, and we've got the values, the weights on these 8 stocks that give us each of these expected returns of 2 to 13% with these smallest possible standard deviations. We found the minimum variance portfolio here. We found the mean variance efficient portfolio here, which maximizes the Sharpe ratio, and which we can see graphically on the other graph that is there. So this is an important spreadsheet, okay? One that you should understand how all of this stuff is being done. So I would encourage you to play around with it. Maybe spend some time putting one together yourself, okay, that uses different stocks. Everything on here you should be capable of doing. I will probably not, I'm sure I will not ask you to do it for this many stocks, but for a smaller number of stocks, yeah, you might see that at some point in time in the future. But at any rate, hopefully this has been helpful for you.